When we talk about thermodynamics, we talk about how stable or how strong bonds are and how stable the metal complexes are. Kinetics talks about how fast these things form or how fast they react. And it's important to understand that thermodynamics and kinetics are independent but related. Before we go into the kinetics, let's do a quick review about thermodynamics. So we talked about thermodynamic trends in metal stability constants and specifically in the stepwise formation constants. And we talked about the trends in these formation constants, the values of K, where the first formation constant, the first stepwise formation constant, is always greater than the second, which is greater than the third, and that's a general trend. And when you see exceptions in this trend, it indicates changes in electronic structure. And this is often related to ligand field stabilization energy. So changes in the electronic structure that result in favorable or increased ligand field stabilization energy would give you a higher value for the later formation constants, and unfavorable changes in the ligand field stabilization energy that decrease the amount of ligand field stabilization energy upon binding of a ligand would give you a lower value than you might expect for the later formation constants. We talked about things that affect thermodynamics, these things that are trends or considerations. So I'll list these here. There are several things that affect the thermodynamic binding constants. Although we talked about it last, one of the most important things is ligand field stabilization energy. And we see this in the Irving-Williams series. So ligand field stabilization energy is an important consideration. Ionic size of the metal. We talked about how higher charge density, which means a higher charge or a smaller radius, can give you stronger electrostatic attractions between the positive metal center and the negative electron density of the ligand, which is just the Lewis base. And in some cases, this is counterintuitive or opposite of what you might expect from hard, soft, acid, base theory. So you have to weigh these things all into consideration. And the third thing that I'll list here is hard, soft, acid, base character. So that's a consideration. We also talked about the chelate effect and the macrocycle effect. And this is just that the stability of a chelate complex or a macrocycle is going to be greater than the stability of any comparable monodentate ligands, or for a macrocycle, the macrocyclic ligand will have a greater stability than the non-macrocyclic similar ligand. So we're going to find that some of the same considerations are used in kinetics, but it's important to understand that kinetics and thermodynamics are not necessarily dependent on each other, but some of the thermodynamic considerations affect kinetics. So now we're basically starting the last part of this discussion on thermodynamics and kinetics, and we're going to focus on kinetics. And the first thing I want to do is look at an example, and I'm going to look at the ligand exchange reactions for some hexa-aqua metal complexes to form hexaamine metal complexes. And let's look at the rate constants of these different reactions. So here I have three hexa-aqua metal complexes going to three different hexaamine metal complexes. And in all cases here, the reaction lies to the product side, and so the product is more thermodynamically stable than the reactant. So I'm going to label the product side as the favored side, or the more thermodynamically stable side. So these actually have very similar equilibrium constants for all of these reactions. But if you look at the rate constant that I've listed, you can see that they're very different. The first reaction happens in less than a minute. The second reaction is very, very slow. So it might take hours for this to occur. And the third reaction is very fast and it happens in a matter of seconds. So once again, we have three reactions here. All of them are thermodynamically favored for the product side, but one can happen in a matter of seconds, whereas the other one can happen only in hours. So what is going on here? So what makes these complexes so different in their rates of reaction or their rates of complex formation? So the next thing, so now what we're going to talk about are these factors that affect rates of reaction. But first, it's probably a good idea to define the terms that are used to describe rates of reaction. So let's do that now. So when something is fast, we say that it's kinetically fast. And the technical term for something that's kinetically fast or something that happens very, very quickly is labile. These are usually things that happen in less than a minute. So reactions that happen in less than a minute are usually described as labile. Things that are kinetically slow are called inert or non-labile. And there are so the kinetically slow things are things that usually happen after hours. And then we have an intermediate. So if kinetically fast things happen in less than a minute and kinetically slow things happen in over an hour or so, then there's an intermediate state there that we basically just describe as intermediate. So now let's talk about the factors that are affecting the rates of reactions, and let's list them. The first thing I'll list here is ligand field stabilization energy and electron configuration. And this is probably the most important consideration if you're trying to predict whether you have a labile metal complex or a non-labile or inert metal complex. So this is where kinetics is linked to thermodynamics, because if something starts out very stable already, it doesn't like to change. And the fact of the matter is it has to change in order to react. So the problem is that if a complex wants to react or exchange a ligand, it has to change its geometry in an intermediate or transition state. And if it's already very stable, it doesn't like that transition state usually. So the inert complexes are the ones that often have the most stable electron configurations. And we're going to talk mostly about octahedral geometries in this case. So they're the ones that we know that have high ligand field stabilization energy. On the other hand, the kinetically labile complexes are the ones that have lower ligand field stabilization energy. And so you can actually recognize these kinetically labile ones pretty easily because they're the ones that usually have electrons in the higher energy orbitals. And for an octahedron, that means that they have electrons in their EG set. So let's look at two examples, one of a kinetically labile complex and one of a kinetically inert complex. And I'm going to use copper D9 or copper 2. So this is copper 2 plus, and this is a D9 metal ion. Of course, you know that it doesn't really exist as an octahedron because of Jan Teller. But here I'm going to label my EG star set. You can look at it as an octahedron, or you can split the energy levels into what we know would be a Jan Teller distorted octahedral or a square planar molecule. Either way you look at it, there are electrons in these higher orbital or higher energy orbitals. And this is destabilizing the complex. In fact, copper 2 plus is very, very labile, and so it usually exchanges ligands very quickly. On the other hand, if I look at cobalt 3 plus, which is a D6 low spin complex in most cases, so I've drawn here a big delta, that's a very stable electron configuration, and so you would expect this cobalt 3 plus complex, and any cobalt 3 plus complex that has a low spin configuration is actually very stable, and we would say it's also inert. Another electron conformation that's very inert is chromium 3 plus, or a D3 electron configuration. So once again, in this case, we don't have any electrons in these higher energy orbitals, so they're empty in both of these cases, And so there's a lot of ligand field stabilization energy in these complexes. They're very stable electron configurations, and they're rather inert. So our inert thing, or our inert metal complexes, are those that have a lot of, those that do not have electrons in these higher energy orbitals. And this comes again from the fact that for a complex to react or exchange a ligand for another, it has to change its geometry. So I'm going to write that down here. So again, this is one place where the kinetics and the thermodynamics are linked, because the more stable your starting material, essentially, the more unfavorable it is to go and change in this intermediate or transition state that must occur in order for the reaction to happen. So our inert complexes are usually those that have electrons only in the lower energy set in an octahedron, and the labile complexes are usually those that have electrons in those higher energy e.g. stars in an octahedron, and this can be extended to other geometries as well. The higher energy orbitals being occupied makes complexes more kinetically labile. So let's apply this to guess how you would classify all of the metal complexes from D1 to D10. So I'd like you to go ahead and pause the video now. What I'm asking you to do is basically guess or use the ligand field stabilization energy to guess how you would classify D1 to D10 complexes. So put them into three categories. We'll have a category for slow reactions, or those that are inert, a category for intermediate, and a category for fast, or labile. So what I'd like you to do is pause the video here and organize D1 to D10 metal complexes into these categories, and let's see if you can guess correctly. Alright, so for D1, whether you had a high spin or a low spin complex, you would only have electrons in the lower energy set. But in this case, it's still not giving you a lot of ligand field stabilization energy, having just that one electron. And so it turns out that the D1 are actually quite fast to react, and they are typically labile. The same thing is for D2. So once again, you have only electrons in those lower energy sets, but there's only two of them. And so it's just not quite enough to stabilize the metal complex to the point where it doesn't react. So D1 and D2 are typically labile metal complexes. Now when we get to D3, now we have, this is the tipping point basically. This is now where you have enough ligand field stabilization energy. The D3 actually react very slowly, and they're classified typically as inert. D4, now it depends on whether you're dealing with high spin or low spin. So the high spin case, here you have an electron in this higher energy orbital, and you can kind of think of it as canceling out one of the electrons in the lower energy orbitals. It wouldn't exactly do that mathematically, it doesn't evenly cancel out, but what this does is it ends up putting it into the labile category. So for high spin D4, you will have a fast reaction or labile metal complex. For low spin, now you've just increased your ligand field stabilization energy. So as you might have predicted, based on what we just talked about, the low spin D4 is a slow or inert complex. Slow reacting or inert complex. For D5, again, it depends on whether you're high spin or low spin. For the high spin case, you are basically in the same, you're in the same boat as you were for D4, but in this case, you actually do completely cancel out the ligand field stabilization energy. So there is no ligand field stabilization energy associated with the high spin D5, and so high spin D5 is a labile complex. Whereas low spin D5, again, you've increased the ligand field stabilization energy. So low spin D5 is actually an inert complex, and they are very slow to react. D6, if it's high spin, again, you're in the labile category. And for low spin D6, now you have the maximum ligand field stabilization energy possible, and so you may be able to easily predict that that would be a low spin inert complex, or a very slow reacting complex. All right, let's move on to D7. So in the case of D7, in either case, now you have an electron, in both cases, high spin and low spin, both have electrons in their higher energy set. And it turns out that no matter whether you're high spin or low spin, D7 are usually fast to react. D8 metal complexes, now it depends on what kind of D8 metal complex you're dealing with. If we have a high spin metal complex, now normally high spin D8 is not in the octahedral geometry. In fact, I'm going to put it here in the intermediate category. It's kind of an odd duck. High spin D8 is usually tetrahedral, and almost the only example of this is nickel 2+, when it's bound to weak field ligands. So when you have high spin D8, usually you actually have a tetrahedron, and that is an intermediate, in the intermediate category. It has intermediate reactivity. If you're a strong field D8, again, you're not usually in this octahedron, but even if you were in the octahedral category, you might expect it to be a fast or labile reaction, but typically these distort into a square planar geometry. And so for strong field, I'm going to call it low spin. So for strong field or low spin D8, again, we're usually dealing with a square planar molecule. And these strong field D8s don't fit into the diagram that I drew down here. They are usually very inert and slow to react. So D8 is kind of our odd duck, and it's actually the only one that's categorized as an intermediate. D9, it doesn't matter if you're high spin or low spin, they give you the same electron configuration. And D9, now you're putting more electrons in the higher energy orbitals. So as you might expect, you have labile complexes that react quickly. And same thing for D10. Now you're canceling out all your ligand field stabilization energy, and so you don't have any thermodynamic barriers to reaction, and so there's less activation energy, and that makes the D10 very labile complexes that undergo very quick reactions or fast reactivity. So I don't want you to have to memorize this information. I want you to understand it so that you could solve a problem and predict the reactivity of a metal complex by understanding its electron configuration here. So knowing about this, knowing about the geometries of the metal complexes and their electron configurations will help you to make these predictions without memorizing. So ligand field stabilization energy is the first thing, the first factor I wanted to talk about here. The second factor is the size or charge of the metal ion. So once again, we're talking about charge density. So to talk about the size and charge of a metal ion, the first thing I want to look at is a trend of three metal ions that have similar size, but they increase in their charge. So the three metals I'm going to look at first are sodium +1, magnesium +2, and aluminum plus 3. So again, these guys all have similar size, but there's an increase in the charge going from left to right here. So it turns out that the higher the charge, once again, the better the electrostatic attraction. So we talked about this earlier when we were talking about thermodynamics. The higher the charge, or the higher the charge density, the better the electrostatic attraction between the metal ion and its ligands. And so it turns out that you will have trends in reactivity, or the rates of reactivity, where higher charge will give you slower reaction. And this is electrostatic attraction. So I'm not classifying any of these as inert or labile at the moment. I'm just trying to look at the trends that I can observe in my reactivity. So I want you to be able to put things in order. Now I'm going to look at some metals, 3 metals that have the same charge, but the radii are different. So the radius of strontium is 1.2 angstroms, the radius of calcium is 0.99 angstroms, and the radius of a magnesium ion is 0.66 angstroms. So here I'm increasing the charge, I'm increasing the size going from right to left. And so that means as I'm increasing the size there, I'm also decreasing the charge density. And so the charge density actually increases going this way, just like the one above it. So I'm going to write kind of between these guys, we're increasing charge density. So once again, as you might expect, strontium reacts fastest and magnesium is slowest because magnesium has the higher charge density. And so again, it can have better electrostatic attraction with its ligands. And so that just gives it a slower rate of reaction. So knowing that the charge density of the metal ion is important, now I'll tell you that these on the left are fast. These metal ions typically react fast. They have lower charge density, and that just means they have a lower ratio of the charge divided by the radius, and they are classified as labile. On the other hand, the ions on the right react slowly. They have high charge density, and they are classified as inert. And the ones in the middle are intermediate. So those are the 2 considerations that you can make for the rates of reaction. You can consider the ligand field stabilization energy, and you can consider the size and charge of the metal ion. There are some generalizations I want you to know about, and I'm going to list them now. And these are overall generalizations. In general, the S block metals are very labile, with the exception of magnesium 2+. So in this general area, I have labile metal ions, except for magnesium 2+. And magnesium 2+ is pretty inert in most cases. So I'm going to highlight that here. That's magnesium 2+ on my really bad sketch of the periodic table. The other thing that you can pretty much count as being very labile are the D10 metal ions. So these are things like zinc 2+, copper 1, and mercury 2+. These things are very labile, and so I'm going to color them in over here. So zinc is here in the first row of the row of the transition metals. Copper 1+ is also there, and mercury. And so you might expect cadmium to also be, which is here. But these are things that you run into pretty often in a chemistry lab. Anything else that has a full D shell is going to be labile. The lanthanides and other F block metal ions often are pretty labile. Anything else that has a full D shell is going to be pretty labile. The liquid field stabilization energy considerations that we talked about earlier, remember that the bigger the delta, the more liquid field stabilization energy you're going to have. And these 3D metal ions that are in the first row of the transition metals, or the third row of the periodic table, no, fourth row of the periodic table, these are the 3D metal ions. And the 2+ of those, remember that those are usually high spin. And when they're high spin, they are usually or generally labile. And that's because they just don't have a very big delta. And so an example of that is copper 2+. It's very labile. This is one of the most labile metals that we deal with in the transition metals. So the 3D metals have small deltas. The 4D and 5D usually have larger deltas, and these are usually the things that we think of as lower spin. And so it turns out that they are mostly inert because they have higher ligand field stabilization energy. So as you increase delta, you decrease the rates of reactivity. Once again, along with that charge density argument, if you have a 2+ metal ion, the rate will be faster, or it will be more labile than a metal 3+. It will be more labile than a metal 3+. So this is labile over here, and this is more inert. Not necessarily classified as one or the other, but one is more labile and one is more inert. So these relative terms, this is what I'm talking about. And it's very common for D3 and D6, low spin, to be inert. So I gave you the example above of chromium 3+ or cobalt 3+. Another common one is low spin iron 2. And this one, so the low spin iron is a little bit of an exception to number 4. Number 4, but remember that number 4 says that it's a high spin. When high spin metal complexes in the first row of the transition metals are generally labile, that's still true. Iron 2+, when it's low spin, of course you would expect that one to be inert. Okay, so that's all I'm going to cover for thermodynamics and kinetics. The next thing that we will move on to is mechanisms of reactions.